All right, in this video, we're going to look at an example that will help us understand that the net work is either the magnitude of the net force times the magnitude of the displacement times the cosine of the angle in between it, or the sum of the x components and y components of f and x multiplied together. So let's look at an example. So let's take two vectors, f and d. So we're going to use the grid here in terms of our relative magnitude. So f is up and to the right. It's got a delta x or an f of x of positive 3 and an f of y of positive 3. And then d is down and to the right, so it has a dy of negative 2 and a dx of positive 4. So if I calculate out the following values, I get that the magnitude of the overall force is 4.24. These are the two components. The magnitude of the overall displacement, 4.47. These are the two components. Okay, so now we want to try to show that this is equivalent to this from our last video. So let's go ahead and calculate it. The first thing we need to do to calculate the magnitude of the force times the magnitude of the displacement times the cosine of the angle in between the two vectors is determine theta. So by determining the theta from the x axis here down to d and the x-axis up to f, I added those two angles together and I get 71.57 degrees. So let's calculate f, magnitude of f times magnitude of displacement times cosine of the angle. So my two magnitudes from above, 4.24 newtons, 4.47 meters, and then the cosine of 71.57 gives me 6 Newton meters, or we know a Newton meter is a joule. Now let's do it component way, the component way. So based on components, we know the x component times the x component for the force and the displacement plus the y component times the y component should give me the same result. So we sub in our components, f times d for our x and f times d for our y. Now notice, remember in the previous video I said just put in the values, whether they're positive or negative, and it will turn out. So since the force is positive and the displacement is negative here, that becomes negative work. So I get 12 minus 6, and voila, I get the equivalent value of work done. And so there's an example that shows either way of calculating the total work done is equivalent. Now, we could also say, since the net force is parallel to the acceleration and directly proportional, it would follow that I could break the acceleration vector when I have, if I sub in for net force m times the acceleration vector, a times dx would also be breaking the components a x times delta x plus a y times delta y. And that'll be important when we get to Ewok.